Welcome to Oddly Real. I'm Nem Stefanovic. One of the most fundamental situations in physics involves dealing with an object with mass moving through space. We say that a moving object has momentum. Momentum is what makes a moving object want to hold its course through space and not deviate from its path. Momentum is also responsible for delivering an impact when the object collides with another. Energy is another foundational concept in nature. Energy is one major component of what moves the world. It is responsible for everything from the motion of particles to chemical reactions to the phenomenon of light and even the existence of massive objects themselves. Both momentum and energy adhere to strict rules of conservation in the universe. For example, two objects that collide may transfer their momentums, but the total momentum must be preserved. Additionally, we know that energy is neither created nor destroyed, only changed in form. These rules form the core basis for our reality, and historically, they've been treated as two separate and distinct phenomena. Yet, there is a deeper connection between momentum, energy, and mass that goes beyond three-dimensional space and can only be explained properly in four-dimensional spacetime. It turns out that momentum and energy are two sides of one single four-dimensional entity called momentum energy, or Momenergy. Momenergy is tied to the very fabric of spacetime itself, and it too obeys a law of conservation of momenergy. In fact, there's a fundamental connection that links momentum, energy, and mass together in one single elegant unification. One of the most basic situations in physics is describing an object with mass that is in motion. Classically, we've used the term momentum to capture the behavior of a physical body with some mass m moving through three-dimensional space with a constant velocity v. Momentum is explicitly defined as the mass times the velocity of an object. Intuitively, momentum is an object's tendency to keep moving as it is and not deviate away from its course. Objects that have more mass or velocity would have more momentum, and thus it would be harder to change their speed or direction. Conversely, objects with less mass or slower speeds would have less momentum, and they can be more easily deflected from their trajectories. In order to change the path or speed of a moving object, we apply a force. It requires much more force to significantly alter the motion of an object that possesses more momentum versus one that has less. Momentum also obeys a universal law of conservation that requires the total momentum of a group of massive objects to stay constant, regardless of how they collide and interact with each other. For example, if two objects collide, momentum may exchange between the objects, but the total momentum before and after the collision must be the same. Whatever momentum one object gains, the other must lose. Another core basis for our reality is captured through the notion of energy. Energy is something truly amazing, since it is not just a core tenet of physics, but is foundational across all sciences, regardless of the subject area, like physics, chemistry, biology, and even more modern topics like computing. Energy is truly universal. Specifically, energy is both an abstraction and something physically real. For example, when an object is moving, we can compute an energy associated with that motion called kinetic energy. Similarly, if you lift an object off the ground, you can compute a numerical value called potential energy, or a stored energy due to the object's position relative to the ground. We know there is energy present, since if we release the object, it starts to fall, losing that potential energy, but gaining kinetic energy. This energy isn't something visible in the object, yet we can compute it as a value associated with the object. However, energy also physically manifests itself in things such as photons of light, which have no mass and only consist of vibrations of the electromagnetic field. Even a body with mass that is at rest, not moving, has energy just because of its existence, since mass itself is another form of energy. Our universe imposes a strict requirement to ensure energy is neither created nor destroyed, called the law of conservation of energy. Although energy exists in a wide variety of forms like kinetic, potential, electromagnetic, heat, chemical, mass, and many others, energy is still ultimately conserved. If energy is lost in a process, that loss of energy is accounted for in the conversion of that lost energy into another form. For example, consider a pendulum consisting of a mass attached to the end of a string, and assume no frictional losses. When the ball is lifted using energy from a human hand to lift the ball higher, the ball gains gravitational potential energy. Muscles had to convert chemical energy within the body into gravitational potential energy, and the source of the chemical energy originated from food that was eaten. When the ball is released, it will start converting its potential energy into kinetic energy to set the ball into motion. Note that when the ball reaches the lowest position at the bottom of the pendulum, it has exhausted its potential energy. The law of conservation of energy ensures us that the energy could not have been lost, and it must have been converted into another form of energy. In this case, that energy is in the form of the kinetic energy of motion of the ball. The ball is now traveling at its fastest speed. From this point, there is yet another conversion of energy as the ball now makes its way back up, turning that kinetic energy back into potential energy and slowing down as it does so. Historically, momentum and energy have been treated as two completely separate and distinct phenomena. Momentum describes a body in motion, and it has its own law of conservation. Additionally, energy is something separate and more general from the mechanical motions of objects, and it too has its own separate law of conservation. So, what's the connection between momentum and energy? The classical concepts of momentum and energy are based on the notion that space and time are separate and distinct. However, our true reality is actually embedded in a four-dimensional space-time, where space and time are not separate and distinct, but intertwined. We, as observers in our universe, see and measure space and time separately based on our particular frame of reference. Our frame of reference is based on whether we are at rest or moving at a constant velocity relative to what we are observing. This is very important to understand because depending on our frame of reference that we are in, we will obtain different values for our measurements. The calculated momentum and energy of a body will be different for two different observers. Note that all of the rules of physics and the laws of conservation will still hold regardless of the different momentum and energy values. The momentum and energy for a physical object are actually two sides of a more general four-dimensional entity known as momentum energy, or Momenergy. Momenergy is something that exists independently of any reference frame or observer. It has a reality all its own, which makes it more real than what we can observe as momentum and energy separately. The momenergy of an object is just its mass moving in a direction in four-dimensional space-time. Momenergy has three components directed in space and one component directed in time. It is difficult to properly visualize a four-dimensional object, but we can look at it in a simplified version if we assume the momenergy component of one dimension of space is 0. In this case, we have two dimensions of space in the horizontal plane with one dimension of time pointing upward. Momenergy has a magnitude, its length, which is the mass of the object. Additionally, momenergy has a direction, which is its orientation in space-time. The direction is always pointed along the world line of the object, which is its path through four-dimensional space-time. When we view momenergy from the perspective of an observer in their frame of reference, then the space components of Momenergy appear as momentum, p. The momentum of each component of space along the x and y axes are px and py, respectively. The time component of Momenergy appears as energy, E. Recall that the magnitude of Momenergy is the mass of the object. In our world, which is in four-dimensional Lorentzian spacetime, there is one elegant relationship that links the mass, momentum, and energy of an object. This relationship is the mass squared is equal to the energy squared minus the momentum squared. Notice that mass is constant, so if the momentum of an object goes up, that means the energy of the object must also go up to ensure that the same value is held for mass. If momentum goes down, that means that the energy of the particle must also go down. Something interesting happens when momentum is zero, which is what happens if the object is at rest. Notice that energy does not go to zero. In fact, energy in this case equals the mass. What does that mean? It means that there is energy associated with the existence of the mass itself, regardless of its motion. But wait, we just said that the energy of an object at rest can equal its mass. However, aren't energy and mass completely different things? They don't even have the same units of measurement. Mass is measured in kilograms, while energy is measured in joules. It turns out that mass and energy can indeed be measured using the same units. The reason why we use different units, kilograms and joules, for mass and energy respectively, is due to historical reasons, when people didn't know there was a connection between mass and energy. There's a deeper connection between the two that is woven in the fabric of space-time itself that makes this possible. Space and time are components of one four-dimensional medium called space-time, and the dimensions of space and time can also be measured using the same units. For example, we naturally measure space in units of meters. It is only for historical reasons and convenience that human beings have measured time in seconds. However, time can also be measured in units of meters. Units of seconds can be converted into their equivalent units of meters simply by multiplying the time by c, the constant of the speed of light. The speed of light turns out to be nothing more than a conversion factor to change seconds into meters for a more natural comparison between the dimensions of space and time. So how does measuring space and time in the same units relate back to measuring mass and energy in the same units? Take, for example, the formula for kinetic energy, or the energy of motion of a moving object. The classical formula is energy equals 1/2 times mass times the velocity squared. This has units of kilograms meters squared per second squared, or just joules. The velocity term v is classically measured in meters per second. However, instead of using seconds, we can use meters, which then makes the units of velocity equal to meters per meter, or unitless. Then the units for kinetic energy simplify to kilograms, which is just mass. This is also true for momentum, which is classically defined as mass times velocity, which again results in having units of kilograms. One important thing to note here is that despite mass, energy, and momentum all having the same units of measurement, they're not the same thing. However, they can be compared together on an equal footing to show their relationship. Similarly, space and time are not exactly the same thing, but we can compare space and time together as component dimensions in spacetime. In the case of Momenergy, mass is the magnitude or length of the Momenergy vector, while momentum and energy are the components of Momenergy along the space and time axes, respectively. Lastly, it is worth noting that the classic formula for momentum, which is mass times velocity, or the classic form for kinetic energy, which is just 1/2 of mass times the velocity squared, are only approximations to the correct formulas. These classic formulas only work for small velocities relative to the speed of light. When the velocities are very large, approaching the speed of light, the formulas are no longer correct. The actual formulas are as follows. Momentum is not just mass times velocity. It has an extra term in the denominator. But if the velocity is very small, much smaller than the speed of light, the formula becomes approximately equal to the classical form, mass times velocity. The classical formula for kinetic energy for a moving object, 1/2 times the mass times the velocity squared, is only an approximation that works for velocities much lower than the speed of light. The accurate formula for any speeds is this one. Finally, the formula for the energy of an object is the following. Look at what happens when we set the velocity equal to 0, when the object is at rest. We're left with one of the most famous equations in science, E equals mc squared. This is the formula that demonstrates that mass is a form of energy. It also shows the immense amount of energy contained within mass, since converting a mass into energy means multiplying by c squared, which is an enormous number. This type of energy is released in large amounts through nuclear reactions or matter-antimatter annihilation reactions. I hope you enjoyed this episode, and remember, oddly real, really interesting.